And without further ado, I think today will enlighten us more about algorithmic perspectives from optimization to control, and welcome. Yeah, thank you.
Thanks a lot, Neil, for a very kind introduction. Great pleasure to be back here. So what I'm going to talk today is about optimization and control. Tell you the truth, it's actually basically what I have learned in the last 1 year. So it's pretty new to me. And given the audience that I also talked today, I could imagine that many things here are trivial, but I hope I could live up to expectation and a little bit interesting things that you might not know about that. Okay, so my talk is about two parts. The main part, so the main theme of my talk today is algorithm. So particularly the focus of this line of research is how we can devise certain algorithm. The first part is more related to optimization algorithm and some inspiration that we got from there. The second part is, let's say, the secondary part. If I couldn't reach here, I'm also happy. But it's some ideas that we got inspired from system theory, where I'm coming from, and then see how we can use it. This is a collaboration with Amin Sharifi Kolarigiani. I'm saying collaboration, but actually this is all due to Amin. He's the driving force of this. Okay. So let me focus on the first part. What is this problem about? It's actually this one equation is everything that I'm going to talk about today. So my hope is to find this G. You can think about it as a nonlinear function, and we are trying to find the zeros of this nonlinear function. You can think about Y is the solution that you are interested in, and you want to solve a zero or finding one, not necessarily the unique one, but you want to find this zero from this optimization problem. So there are many applications falling into this category, in particular that you are also quite familiar with is basically any optimization problem can be translated into this problem. But there is sometimes another facet of these problems that you might see, and that is actually finding the fixed point problem. So it might not be presented like that to you. It might be presented like that, which is basically a fixed point of another operation. But these are basically a very trivial equivalent of one another. And the only way that you go from one to another one is that to replace this nonlinear function with identity minus the other one. So if you have an algorithm in this world, the only thing that you need to do to solve a problem from that one is just replace the G function with identity minus the operator tau, and you get an algorithm in another board. This is a very trivial transformation, and it can go also backward. It can be vice versa. So basically, when we are talking about solving a fixed point problem or finding a zeros in a function, they are pretty much the same thing. And so this is the problem that I'm going to talk throughout the first part of the work. And this is what you can actually be the big picture that you want to remember is that the problem is either root finding or fixed point problem. And along the way, we have two settings for this one particular problem. Either I call it exact oracle, and I try to stick to this color code blue and red throughout my talk, is that the blue part is basically the exact oracle that I have exact access to either G or tau. And when I'm trying to devise an algorithm, I have access to this guy. Or it might be an inexact setting, which basically I do not have access to the tau, but I have to an approximation of the tau. You can think about it as a random or a stochastic version of tau. And then the only, let's say, underlying assumption is the expectation of that is the true one. So you can think about it as unbiased. By the way, there are some details that I might not be careful about it. For instance, for everything that we're going to say is that the second moment of this has to be bounded. But I hope you forgive me for that. But in the relevant papers that I'm going to cite later, these are precisely mentioned. So this is basically the problem, two different settings that you might be interested in. And when I'm talking about algorithm, basically all the algorithms that you can think about it as updating the approximation that you have yk by a certain direction. And just be more precise what I mean by exact oracle here and inexact is basically the direction that you update your solution is going to be either as a function of this or it's going to be a function of the approximation of that. So this is basically the big picture. And this is as old as optimization algorithm literature that you know more than me. And back to the first point that I said the last year, it came to my attention, I found it interesting, and I want to share with you, is that there are many algorithms that are developed in root finding, and then you can actually translate it to the fixed one and vice versa through this simple transformation, and they could connect to one another. And I was not aware of that till last year that it came to my attention. So let me just go a little bit, basically a little bit literature review of what we could think about these two class of problems. I started from optimization because we might be more familiar with the names here. So if you think about the optimization problem, that's the kind of problem that we are interested in. So we have a problem, we want to find the optimizer, and the function that we are interested in is either available exactly to us like f of x, or it might be expected of a function for which we have f, the approximation of f. And when we are thinking about x star, there are two ways to characterize x star depending on the information that we have. So the equivalent characterization is either the gradient of that is equal to 0, or let's say the expectation of the gradient equal to 0. So these are equivalent, and the distinction is really based on whether we have information about f or a random version or a stochastic version of f. And then this is the oracle that I mentioned earlier, that it's going to be a function from the same space that you are searching to itself, or a random version of that, or a stochastic version of that. Basically, if you look at the literature, this is the deterministic world, and that's the stochastic world. So this is one, let's think about the class of problem that usually we know as a root finding problem to zero problem. When you look at the control problem, what you might be interested in is finding this infinite horizon problem, where you optimize over the policies, and this is something that we call it as a value function that we are interested in. And the value function is a function of the initial state that you have, and this is a discounted cost, and this is a conditional of initial condition that you are solving. This is the problem we are interested in, and then we are optimizing, and this value function is something that we are interested to find it. To make a clear comparison, I assume that S is just finitely many, so we are in the finite state world. So this is basically a vector. And I'm saying because I want to be comparable with a decision variable in optimization. So in control problems, you can actually characterize this guy through a fixed point operation. That's, you can find different names, but in control literature, you can think about under the cover of model-based or dynamic programming. And this is the equation that characterizes this V star that we are interested in. The connection of the tau, which is the operator, the Peyman operator that characterizes the vector that we are interested in, to the data that you have here goes through this one. If you already have seen this one, this is, you are very familiar, but maybe the only thing that matters for the algorithmic aspect throughout my talk is that this, you can think about this as an operator which is piecewise linear on the vector that you are interested in. This being piecewise linear is going to be important later for algorithmic aspect, but it is a nonlinear one, and the solution that you are interested in is going to be a fixed point of that. And the operator is going to be it's going to be a vector with the size of the number of states that you have to itself. So these are very classical things. What was less familiar to me before this correspondence is the stochastic counterpart of this determinacy, which sometimes we refer to it as the model-free, and it's going to be the main objective of the reinforcement learning problems. And then basically, we want to solve that model-free column. The interesting thing is that this is what is very well known as Q function. This operator is not necessarily the random version of that. So there is a little bit discrepancy between this optimization and world. So if you think about from the beginning, here is the optimizer you are interested in. Here is in the optimal value. So it's a little bit some differences. I will comment on that later also. But the interesting thing is that what you are interested in is going to be a fixed point, either this operator or it's going to be expected random operator. And then depending whether you have access to tau or you have access to tau hat, it's going to be different algorithms coming out of it. So the share part is going to be characterization. The information might be different depending who you have. And the operator, the random operator, also has a very similar nature of that. It's going to be, again, piecewise linear. Now, if you look at this big picture, having said everything that I said, you see a one-to-one correspondence between these two worlds. The first one, if I have, back to the very first slide that I showed you, if you have an algorithm of the solving this gradient equal to 0, if I change this oracle to identity minus psi, I should be able to get an algorithm in the model base. And vice versa, if you have an algorithm to solve a fixed point, you should be able to get an algorithm in optimization world by just replacing identity minus gradient of f. So wherever you have tau in that world, you just replace it that. And with the same logic, you can also make it a one-to-one correspondence between the stochastic and the model-free one. So this is a big picture of somehow making analogy between optimization algorithm and control algorithm and how we can translate one to another. So by looking at it, it was interesting to me to see what are the link between the algorithms in the literature that we are familiar with. And I found it personally interesting, and I just want to share with you some of these correspondences. You might know already many of them. So let me now, I want to focus on the blue part, just to give you some connection between the algorithms in optimization world and the model-based control. So what, just to remind ourselves again, the problem is going to be a root funding, and the algorithm is basically this. So when I'm talking about different algorithms, it's all about how the decay is going to be generated or it's going to be introduced. And then if you are talking about optimization, the oracle that you have is going to be the gradient of f. And if it's about model-based, it's going to be the v minus identity. This is kind of reminiscent. I mean, this is what sometimes we call it Bellman residual as well. This is the residual that we want to force it to 0. So I'm pretty sure you all familiar with gradient descent. That's the basic algorithm that we have. And if you put a scalar version of decay, we basically get the gradient descent. So this law is going to be gradient descent. And there are other versions of that, and accelerated version of that, and like Nesterov of Polyak, where decay looks like what you are seeing here. From a control perspective, what I found it personally interesting is that when you write down these things, there's a dynamics going on the y side. When you write it like that, there's a dynamics on the d side as well. So for me, it was very interesting that how a first order dynamic in the direction that you update accelerate the process. Things become even more complicated here. Don't ask me what's the difference here. I personally implemented both of them. I saw the acceleration. I personally, not because Niall here, but I found Nesterov more effective, but just in the limited experiments that I have. So these are what we very much familiar, and I'm sure you are familiar with that. For me, it was also interesting to see what happened on the algorithm side. So the only thing I did, instead of here putting the gradient, I put the Bellman residual, and it turns out that all these algorithms that you might have heard in control problems have exactly the same correspondence here. So if I put this gradient, it's going to be gradient descent, but value iteration is exactly gradient descent in which we replace this guy instead of gradient. So that's what I found it interesting. There are also two versions of accelerated VI and momentum VI, for which the only difference is exactly which type of update rule you pick up here. There are some non-trivial discussions about alpha k and beta k as a step size. To me, it's less complicated when we are in deterministic, but when you go to the stochastic, things become more complicated. I'm going to comment on that. But these are basically more of first order algorithms that you might have seen in the literature. There is also another very important class, which we go beyond looking at only gradient. We want to look at the second order information, which I just denoted by H, which is the Hessian of the F, or let's say a Jacobian of this object in the control world. It's a little bit basic algebra to see how this comes out of the derivative of that, but it's not difficult to see that the Hessian can be computed like that, where P is the transition probability matrix under V policy. But what is important is that if now we look at the most common algorithm in the optimization literature, Newton method using it, it looks like that. And this is the Hessian that we use. But if you want to translate this, the only thing I need, instead of G, I put this Bellman residual. Instead of H, I put this Jacobian. And it's interesting that it turns out to be exactly policy iteration. So for me, this is also, but even this dates back to 90, I think, 80s. This is 80, even 76. This connection was there. But perhaps less explored or less looked into it is the stochastic counterpart of that. But you can imagine, I'm not going to name all of them one to one, but by the way, these are what I want to say. So the first three are going to be first order. The last one is going to be the second order. I'm going to comment about the behavior of each of them shortly. But let me, before I discuss about the differences and similarities here, let me go to the stochastic one, which I found it, at least I was less familiar with that. And that was this slide. So this is exactly the corresponding stochastic counterpart of that. We all know that the rule of the gradient descent is going to be the same. The only thing needs to be adapted is going to be the step size. But basically, this is the GD, the stochastic GD. What I found it interesting is that Q-learning that I've seen it 10 times before last year, I've never came to a realization that this is exactly SGD. The only difference is that I put, instead of the gradient of the random gradient of F, it's going to be just the Bellman residual and the Hessian, and just this one replaced. We also have the momentum, SGD. If you look at the literature, there are several options, the accelerated version of the Q-learning. And the difference there are boiled down to the difference of these coefficients, the step size. Just a little bit about the importance of a step size. So when you think about the random setting, if the initial condition Y that you pick up is going to be the actual solution that you want, you can see that you're going to leave it anyway, because the oracle is not exact. So you may get a random version of that, which is not exactly this one, and then you think that you're not correct, and you leave the equilibrium. So even if you start from there, you're going to leave it. So it's very important to pick up this step size in a way that even you leave, you go and come back to that again. So this brings a little bit complication to make sure that these coefficients are right. And actually also literature, particularly when it reaches to accelerated, you see that there are many variants of that. And these three differences are just the choice of these alpha and betas. But apart from that, even in deterministic setting, I have seen very recent activities on designing a step size without knowing the prior information about the function G. Because usually when you devise this kind of step size, you need smoothness or any regularity of the operator that you are interested in. And knowing those values, first of all, by itself is a limitation. And second, it might create a little bit conservative algorithm. How to make that adaptive is also another, to the best of my knowledge, ongoing work in optimization algorithms. So choice of these coefficient could be also important. And of course, we have the stochastic counterpart here. And the stochastic counterpart, this ZAP Q-learning, at least I've seen less familiar comparing, for instance, to Q-learning or momentum Q-learning. This was initially developed by Sean Main, and it was not necessarily exactly in this language, but it is essentially the stochastic Newton method. So ZAP Q-learning is exactly a stochastic Newton method where the Hessian is updated like that. So if everything that I've said so far was about the one-to-one correspondence between optimization algorithm and in first order category and second order category. Next, I just want to give you a little bit feeling about how this category is different than this category in terms of complexity and in terms of performance. So this is first order, versus second order algorithm. So the first order, this was the value iteration. If you forgot what it, and by the way, from now on, I'm just focusing on the control part or reinforcement learning part, if you wish. And I just talk about the algorithms there. And the value iteration, this was, if this is a gradient descent, basically. And the policy iteration, this is a Newton method. So when you apply this in finding a fixed point, the first thing that comes to my mind is the per iteration complexity. And if you think about the per iteration complexity of this oracle, you see that the oracle is n square m. So one time you apply this, where n is the number of states, m is number of actions. And it is a square in general when tau could be random, because it might be going to different states and you have to sum over that as well. So the n square comes from the fact that this might involve some randomness, and m is because of the number of actions that we have. So I have the sad face here, because if you look at here, you not only have this tau, but you have to make some minus here. This minus is exactly the bottleneck in second order algorithm for solving a fixed point. And n cube, if you just want to get a little bit feeling about that, you can think about a control problem with 1,000 states, where we are here talking about millions, and here we're talking about billion number of operation per iteration complexity. So this is really the downside of the second order algorithm. But it's actually very interesting to see how that plays out in performance. So here it's just one example, but I can tell you what I'm showing to you is very typical behavior of these two algorithms for control problem. And also you can see it a similar one for the reinforcement learning. This is just a case with 50 states, 5 actions, and B somehow showed how dense the transition probability matrix is. So from one state, you can go to 20% of other states. That's basically what B means here. And gamma is a discounted factor. So this iteration, if you run the value iteration, it's going to be the green one. And you see, oh, sorry, the red one, my bad. So the red one is the value iteration, and the poly iteration is the green one. So you clearly see a difference in the convergence rate behavior. One is much faster than the other. But that's not the only aspect that policy iteration beats badly value iteration. What is also interesting is when the discounted factor, okay, so this is, this one is a linear convergence, and the green one has 2 convergence guarantees. One is what I wrote here, so locally quadratically converge, but it actually also, we know for this class of problem, MDP, it converges in finite time. So it even has finite convergence, but also local quadratic convergence, so depending which one you like to choose. So it's quite fast. But what is also more interesting, I wanted to say, is dependency of behavior with respect to gamma. And this is also quite important. So when gamma goes to 0.99, you see how it changes the behavior. So the behavior of the value iteration becomes pretty much flat, and the green bond remains pretty much the same. And this actually says something about this algorithm. If you look at how gradient descent converge or value iteration, the analysis heavily relies on the contraction of this tau. So if tau is contraction, then you have linear convergence, but the linear convergence is dictated by gamma. So gamma is really the one that determines the convergence rate. So it's not only about the theoretical bound. Even the way that it converges requires gamma, requires contraction. But somehow this quadratic bond is practically at least independent of gamma. And that's the behavior that it has. Now, what I wanted to say, let's say, where we try to focus on is to somehow combine the property of these two. So whether there exists a version of policy iteration with complexity of value iteration, but somehow share this behavior. And that's what we're trying to focus on that. And this is actually not some new question. If you look at the corresponding in optimization world, the optimization world, they call it quasi-Newton method. So we basically pick up that one also as a quasi-policy iteration. And the idea is all about these metrics. So remember, this is the first order, this is the second order that I wrote. If I change this a little bit, I just write it like V minus t. You see the difference between these two words is basically this guy. If this guy is 0, these are coincide. If not, then that's all the differences that you had seen in the previous example is due to this guy. So the entire point is how we approximate the Hessian. And this low rank is a particular feature that allows us to remain in the same complexity of the value iteration. If it is a full rank and we have to make it inverse, then you have to tolerate n-cube complexity. The question, can you go to stay with the complexity of n squared or even n, and yet approximate this one? So this is called quasi-policy iteration scheme, or you can think about it as an inspiration from quasi-Newton method. What I wanted to say is that if you look at the general algorithm, like gradient descent Newton algorithm, so the way that people think about coming up with approximation of P is the following. When you run the algorithm, you collect the gradient of the function. So you collect the gradient of the function along the way, the first gradient, second gradient at different points. So what you can do, you can actually approximate, using this to approximate the metrics. That's the big picture of how people approximate generally. What we had done is what I just earlier mentioned about the structure of tau. So we look at tau, and then we realize this operator tau, or its Hessian P, has two properties, and we try to exploit these two properties to approximate P. One of them trivially is a stochastic matrix. So this basically, one vector is the eigenvector of the matrix corresponding to eigenvalue 1. And then it also behaves locally F1. This is exactly what I said earlier, that it is piecewise linear. And this piecewise linear also explore. If you put these two equations together and try to approximate this just using this, you can write down a simple quadratic program. And the quadratic program would be something like that. So you just want to optimize, find a P, which is close to your prior. In the work, we just pick up prior everything 1. So this is a matrix, everything 1 divided by the size. And then we solve these two problems. This is how you can interpret it, the closest P to this prior with these two conditions. But what I wanted to also bring to your attention is that this has a closed form solution. And if I pick up the closed form solution and plug in here and compute this guy, what you can see is going to be, this is going to be a rank. Only thing that is updated in prior is two direction is going to be updated. So this rank to update of that, that's particularly due to the property of Frobenius norm here. If you pick up other norms, you might be in trouble. It's not, but Frobenius norm thankfully has this closed form solution. And this is what I wanted to say. That's the end of the story that on the first part. So the quasi-PI coming from this perspective has this update rule. And if you compare this update rule with VI, you see that this direction, there are two other directions that are introduced. So these two other directions sounds to be the one that coming from this perspective. One direction is literally identity, and the other direction is the cost of your model, of a cost of the current cost of the control problem, given the policy that you have at iteration k. That's the meaning of that, the current running cost. These are two directions that you update V. But it's also more important, in my opinion, it's more important to highlight the other step size rules. So these step size rules are also becoming dependent on the V that you have. There are closed form solution to that. And these are, you can think about it as a state dependent or adaptive step size. So you have adaptive step sizes, you have two new directions, and that's basically the new algorithm you can think about it. And if I just want to show you how the performance of this looks like, I want to show you this one. So this is the same MDP that I showed it earlier. So the VI, you see that the number of iteration increases, just to show you. This is the VI, this is the policy iteration. The pink one is the Nesterov one from the table. And the black one is what I showed you earlier. What is the blue one? The blue one, if you pick up quasi-Newton method from the literature and plug in the transformation that I told you, just pure plug-in, that's what you get, the blue one. And it is interesting to see how things changes when gamma increases. So when gamma increases, you see that all these guys start running away, except the blue one and the black one. But the C black one is beating the blue one. for a very good reason. The operator that I'm interested in has two structure that is preserved throughout the space. I'm keeping using that too. So it shouldn't be surprising that it is beating that. But it's also interesting to see that this remains insensitive to gamma. So essentially what is happening in that two direction is that you really update across the eigenvalue corresponding to gamma in a very efficient way. That's my interpretation. You can also implement this exactly to the stochastic setting. A stochastic setting, you always have worse convergence. This is, you can think about Q-learning. This is the ZAP Q-learning, the blue one. And you can see the other two. This is a speedy Q-learning, and this is the one that the black one, similar to the one that I proposed. And that's how the behavior. It is very interesting that the ones that approximate Q, it remains insensitive to gamma, whereas the other becomes worse and worse. So in a way, somehow to mitigate somehow to improve this contraction, the dependence on the contraction. So that's pretty much for the first part that I want to present. I guess I open more question than answer. And I think the most important question that I didn't answer, and I don't have good answer for that, is that, okay, I can translate from one to another one, but can the analysis be transferred from one to another one? And I want to say, at least to my limited experience, it's not as straightforward. And for two reasons, I just want to bring, maybe you can have a good question answer for that. First of all, when you talk about optimization, you have one single value that you care, which is the optimal value. And it usually enjoys convexity. We have a convexity as a very powerful inequality that helps in all the analysis. When you go to the fixed point, you don't have one value. There are two vectors. The best that you have, you can look at the difference between two vectors in a norm and call it residual, but what norm you choose. The choice of norm has a significant impact. And the most important one, the moment, whatever norm you choose, you may lose the convexity. Your operator remains monotone, but the residual that you want to use it as a convergence guarantee is going to lose convexity. Yes, please.
Do you understand this behavior that the blue curve and the pink curve have a gap at 0.9, they have no gap at 0.99, and they have a large gap of 0.99. It seems to either it's atypical or you have a change of behavior which is not.
So I think this is let's say a numerical situation in the. So what blue algorithm does is that along the way that it goes, look at in the past gradients and approximate Hessian. So if you go through a path where you cannot approximate Hessian properly, it may give different behavior. So to answer your question, I think that is a consequence of how blue algorithm approximate Hessian.
It's locally unstable. That's why you get the oscillation.
Definitely not monotone. So definitely in terms of this error bound is not monotone. So it goes up and down. Yes, that's true. By the way, I think to the best of my knowledge, except red, none of them has provable monotone behavior with respect to this norm. Only red has monotone behavior provably. Yeah. So that's, yes. Both of them was one thing, but I tell a second one. Thanks for reminding me. But go ahead, I answer your question. I think it's an excellent idea to look at that analysis. It becomes definitely that context. I agree with you. But what I can tell you is that when you approximate the Hessian with low rank, so you never get the exact Hessian, you always have low rank. The blue one, to the best of my knowledge, does not have even convergence guarantee. We always see nice, but it doesn't. If your Hessian becomes better and better over time, there are general analysis that you have local quadratic convergence as well. Yeah. By the way, just on that point, there's another issue to pay attention to, that the dynamic programming and reinforcement learning operators are non-smooth. So this being piecewise linear could be a potential difficulty. Like the way that non-smooth optimization could be a little bit difficult. So just a potential. But the second point, which I also found it very recently, I came to know that it creates difficulties, that if you go to, maybe I just quickly go to these two words that if you look at these, when you have optimization, naturally, the Hessian that you have is symmetric. This h of x is a symmetric matrix with nice eigenvalues, totally real eigenvalues, with all nice properties that you might be interested in. When you go to a fixed point operator, this h of e is not necessarily Hessian. That could be also a source of difficulty. So, and I know, okay, I read very recently a paper, please take it with a grain of salt, that Frank Wolf, if you, for instance, add one of these guys here, Frank Wolf, if you have a constraint, for instance, then the corresponding model corresponding fixed point does not necessarily converge exactly because of non-symmetry property of H. Okay. So if you get any progress on this kind of thing, it would be definitely interesting, particularly to prove formally some sort of independence of gamma or contraction property, in my opinion, would be interesting. We didn't manage it. We're still trying, but we didn't have any progress so far. So I was wondering if I can continue for 10 more minutes, or I can also stop here. I present everything. Oh, okay. So I wanted to say something else. This is actually, funny enough, is a little bit older than the other one. And I have to say that it's not all good news, but anyway, I want to share it. Given coming from a system theory control background, I thought maybe you might find it interesting. So far, what did I do? So I have a fixed point operation. I have an operator. I wanted to compute it. I have an algorithm, and I talk about how the algorithm should converge, given the oracle of that operator. The second part, the main attempt in the second part is to look at the oracle and see if I can make the oracle more efficient. That's basically the goal. So this is the operator that I just talked about it earlier. So this is a control, this is the same operator as I was talking about. I dropped the expectation because it's not gonna be relevant. So it's gonna be this operator, and then I have A is a control action, S is the state, and F is where the dynamics pops up. You can think about this as a way of mapping a function to another function, where the complexity of transforming this function to another function is basically nm. Remember, I dropped the expectation here, so I drop one of the n square here. But everything I want to say can hold throughout. I just, for simplicity, drop it. That's not that important. So this is the operator that I have. One time that I operate nm complexity. Now the question is, can I do better than that? So the entire point was an attempt to make one-time operation of this in a better way. So it was initially, actually, I have to say that actually I got motivated about this question first when I read interview by Lasser. He got some SIAM award. I don't know if you heard about Lasser hierarchy in polynomial optimization, but he had an interview and talking about the behavior of these in different domains, and that's actually where I got the inspiration. But before I answer this question, I want to go back all the way to some very old results in system theory and signal processing. So for the time being, forget about what I told about dynamic programming. I'll get back to that. But the way that we look at the linear systems is just this linear time invariant system where we could think about it as a way that we map an input signal U to an output signal Y. So this is the transformation of one signal to another signal. And usually the way that we deal with it is that we actually transfer this one input-output mapping as a convolution operator. This convolution operator is a complicated operator in two ways. The first one is that, first of all, the operator itself is a little bit complicated, involves integration in continuous domain and so on. But also from an information point of view, if you're interested at a single point here, you need the entire history of U to compute the single point here. So in terms of information for one point on the output, you need the entire information of the input. So what was in my opinion, revolutionary in the literature of system theory and also control, is that they start looking at this input-output behavior into another domain, which we call it frequency domain. So what we did is that, what they did is that the frequency domain, they went down, they transferred to another domain, and in the frequency domain, this is so-called frequency domain, the behavior of the linear system as a convolution is turned out to be a simpler one, which is just a simple algebraic multiplication. And this simple algebraic multiplication, for those people come from control background, we call this h of the omega as a transfer function. But basically, instead of looking at the convolution, we look at just a simple transformation, algebraic transformation, multiplication. But not only operationally got simpler, but the first point that I mentioned, that now if you need single point here, you only need a single point in the input in that domain to find out the output. So that was a revolutionary idea, and it's basically backbone of many of results that we have in system theory and control. But now back to the operation. If you really now want to bring this back up, you still need to again apply this Fourier transform, this operation from frequency domain to a time domain. And that's not necessarily something easy to do. And the complexity of that naturally is n squared, where n is the number of points that you have here and here. And here, something that was interesting, and I just want to share with you, I don't know if you find it interesting, but I personally found it interesting, the history of this Fourier transform over the decades and how it evolved and how it improved. So there was one idea from signal processing to make this frequency transform faster, and that was actually called fast Fourier transform, or FFT. That was a pure algorithmic idea, just looking at how many times you have to do arithmetic operation of summation and algebra, and just basically save some of these computations that are repetitive. And then they go from n squared to n log n. So this just was the pure algorithmic idea. So instead of computing this with n squared algorithmic complexity, they go with n log n. But what I found it even more interesting, at least historically, is how it was actually developed. Initially, the first paper published in 1965 by Cooley and Tukey. Cooley was at IBM and Tukey was at Princeton. But actually, the algorithm, now we know that it was known even 10 years earlier than that, during the Cold War. And they actually used it to spy on the nuclear facilities of Russia, Soviet Union facilities back then. Ironically, after many, many years, sounds not so much far history. And that's now, this is where they develop. And after this, the fast Fourier algorithm found many other applications as well. And actually, in 2005 or 4, was recognized as one of the top 10 algorithms by SIAM review. So that was basically a history of Fourier transform and how valuable it is. But now you may wonder how on earth I'm going to talk about this comparing to the dynamic programming that I was talking about. And let me flash back to the dynamic programming picture that I started with. So this was the operator going from functional space to another function. And the question that we try to look into it is that there is a similar transformation in the functional spaces as well, similar to the signal spaces. And it turned out that there is one good candidate for Fourier transform in the functional spaces. And that's something that we know as convex conjugate operator. So this convex conjugate operator has some interesting similarities to Fourier transform. And for instance, if you look at, this is a so-called unitary operator. So if you apply convex conjugate operator twice to a certain class of function, which by the way we know is convex functions, you translate to the function itself again. We know that this is also the case for signals as well. So if you apply Fourier transform twice for certain property, L2 and whatever, you get the same function again. So in that sense, they are similar. But there are also other ways that they are not similar. And that is, one is linear operator, the other is nonlinear operator. So that's inherently different. So what was a very elegant idea was developed by these guys, that they actually, also earlier than this work, they knew that if they change the underlying algebra, if they change the meaning of summation and multiplication, you actually go from Fourier transform to convex conjugate operation, discrete convex conjugate operation. So the difference is just definition of summation and multiplication. And these guys use this to actually implement fast Fourier transform for fast convex conjugate transform. So they develop a fast algorithm to compute numerically conjugate operation. But I personally found it extremely surprising, and to this day, I don't know if you found you, please let me know, is that if you look at what I said about Fourier transform, the complexity is n log n. These guys first develop exactly n log n, then they go one step further and it's just n. And I don't know how they actually get faster than fast Fourier transform, why they are inspired by that. But anyway, I found it interesting. But looking at this work, you see just n complexity. So this was the history, and then basically our inspiration to say, okay, now let's look at the tau operator in the conjugate domain. Yes, in the another domain. Yes, correct. But it's not that much different. So the conventional one is summation and multiplication. The other one is multiplication and max. Max of two variables. So it's pretty much the same algebra in terms of computer binary operation. So what we did is that we tried to write down this operator as a function into conjugate domain, the convex conjugate domain. And there are some hurdles, so it's not that we can immediately translate. There are some details, some structure that we need about F, but I skipped those technical details, but the punchline is that we can actually connect and complete this picture. And you can, under certain conditions, compute this operator exactly in the conjugate domain. And with that, we can write down the relationship on the conjugate domain as effectively summation. By the way, I said this is the this summation is in the conventional sense. So in the new algebra, that's multiplication. I always get confused, but anyway, this is effectively summation under certain condition. But being summation, you can also see some similarities. First of all, I told you that summation is the multiplication in new algebra. Transfer function is also multiplication, so you should not be that much surprised. But what I also personally found it interesting is that if you need 1 point of the value function, you just need 1 point on the conjugate domain as well. So that's also, and then what you have to add to that is going to be what defines this tau star. There are more details to that, but I would be happy to discuss it offline. But and then if I use this guy as an oracle for these two operations and just add summation here, then we get actually nm complexity to n plus m complexity. Again, similar nature that n squared boiled down to the linear. So that you can get it. So this is what we had done. So when I was working on this project, I have to say that I was very excited, not because of this, but I knew that, I learned that actually fast Fourier transform also has a quantum computing algorithm for that. So you can actually solve even this using quantum computers in a faster way, even to logarithm complexity. So I was very hopeful that actually we can convince people in quantum computing to use this kind of a structure to develop even further. And naively, we thought that we can go to the Berekov case of dimensionality. And some people took us seriously and from IBM Quantum and then developed this algorithm and they report this result. So it's going to be logarithm n and m. So we were quite excited about that. But I have to say that 6 months after this work by IBM Zurich, some people from Waterloo showed that that result is not correct. And it's actually impossible. And they said the best that you can get a square root of n, and they develop a square root of n. But my knowledge is already finished there, so I cannot give any educated opinion on that. But that was an interesting observation. So since then, I have to say that we a little bit stopped there. But I thought maybe you found it interesting. But one last thing that I want to finish my talk with that is I personally was fascinated with the idea of how to make things faster in quantum computers. And I found it this way, at least that's my naive understanding, is that you're interested in this function. And if you want to compute the function as a whole, you have to accept this complexity. You cannot do more than about that. But what if I can construct a random variable whose distribution looks like that? So if I generate a random variable whose distribution like that, let's assume that these are all positive and it's generated with the but can you use that one to generate the action, and then you have some sort of guarantee? So I really like to push that one, but again, I couldn't do that at the other. It's very difficult to even connect a realization of V with this optimization. So that was also some part an unsuccessful thought process. But anyway, thank you for your patience, and I would be happy to take your questions. And these are the relevant words.